Okay, I thought we'd start with cylindrical coordinates here. For three space, instead of Cartesian rectangular coordinates, this is an alternative system of coordinates for locating points in space or describing points in three space. These are really good when you're dealing with a figure that has z-axis symmetry. Okay, if you take a look at this figure here, you'll notice that the cylinder we're dealing with here that's drawn is actually has what? Z-axis symmetry. This is supposed to be X, Y, and Z. I guess I could have labeled that there. But anyway, there it is. What are cylindrical coordinates? We've got R, theta, and Z. In that order. You have, of course, in any coordinate system, you have to be careful about the order of the coordinates to get the proper meaning. R and theta, this should make you think of polar coordinates. And in fact, R and theta are precisely what you would get from polar coordinates if you were thinking about the X, Y, Z system. Okay, let's come down here. Okay, if you guys look in this picture, you can see here, usually this point would have what? They'd have Cartesian coordinates X, Y, and Z, right? Now, if I imagine that point X, Y, Z there, and I project that point down into the X, Y plane, you can see that the R and the theta here are precisely what you would get from polar coordinates here. Okay, so basically cylindrical coordinates are polar coordinates together with Z. All right, so conversion should be old hat here. You remember from Calculus 2. Conversion from cylindrical to Cartesian rectangular coordinates. The following, we would get what? X equals R cosine theta, Y equals R sine theta, and Z is just Z. Okay? Conversion backwards from Cartesian rectangular coordinates to cylindrical coordinates. Here's one way of doing it. You could say R is what? The square root of x squared plus y squared, and the tangent of theta is y over x for x is not equal to 0. If x is equal to 0, of course, then you would have a point that lies on the xy plane, or on the y-axis, and then it should be easy to solve for there in any particular case. Okay? Now, you guys do remember from Calculus 2, if you've got polar coordinates, R and theta, there's actually what? Those are not unique, right? There's something I call associates for any particular R and theta there. You can do what? You can add pi to that angle theta and negate the value of R, and that would be what? Exactly the same point. It would still satisfy these equations up here at the top. Okay, and you could do that over and over again. Okay, so you could add multiples of theta, of pi to that theta, and you would still satisfy these equations here, but you would have to change the sign on R yet again. Okay, so if you have a particular triple for cylindrical coordinates, then all cylindrical coordinates can be found from that one-ordered triple by doing this here. Okay, all right. N is an element of Z. Remember, Z it's German for Zahlen, meaning integers. Okay? So this is old hat from Calculus 2, really. Okay? Let's go ahead and look at a couple of quick examples here. Convert cylindrical coordinates to Cartesian here. So we've got 6, negative pi over 3, comma 5. Okay? X equals R cosine theta, so that's 6 cosine of negative pi over 3, so that would be what? 6 times a half is 3. Y equals R sine theta, so that would be 6 sine negative pi over 3, so that would be 6 times negative square root of 3 over 2, so that would be negative 3 square root of 3. And then Z, you just read that off, that's 5. So the corresponding Cartesian coordinates would be what? 3, negative 3 square root of 3, comma 5. Okay, so that would be easy. Going backwards the other way is a little harder here. Suppose I convert Cartesian coordinates negative 1, negative 1, 3 into cylindrical coordinates here. Okay, I need to look at the x and y here. Let's go ahead and compute the r value. That's the square root of the sum of the squares of x and y, so that would be what? The square root of 2. Now the tangent of theta would be what? Negative 1 divided by negative 1 is 1. Okay, now that doesn't uniquely determine what theta is here. You have to keep in mind here, the Cartesian coordinates negative 1 would actually be what? In the third quadrant in the xy plane. So the value of our theta there has to be what? An angle whose tangent is 1, but actually is a third quadrant angle. And you would find that's actually 5/4 pi. Notice that, again, we mentioned this in Calc 2, you can't just take tangent inverse of 1, because that always gives you, or tangent inverse of whatever this ratio is, y or x, because tangent inverse always gives you an angle between what? Minus pi over 2 and pi over 2, and that's fourth or first quadrant, right? Respectively. So it isn't that automatic here. You have to do just a little bit of thinking. But there we've done it, okay? So let's talk about all the cylindrical coordinates here. So what? -1 to the nth power times the r, right? And then our angle theta, 5/4 pi plus any integral n times pi, any integral multiple of pi, that's the same n in both cases, comma 3. Okay? So we've got all the cylindrical coordinates that we could wish there. Okay? Now, let's talk about graphs of surfaces of fixed coordinates. Suppose I have r is fixed, and I let what? Theta and z just, run through all possible values here. Do you see what I would get here? I would get what? I would get a cylinder, right? Okay? This would be the set of all points where r is fixed and the other two coordinates are what? Free. Okay? This is one of the reasons we call them cylindrical coordinates. Okay? How about if I fix theta, okay, some constant theta value, and I let the other two coordinates run free here? Do you see I would get what? A plane containing the z-axis, which is orthogonal to the xy plane here. By the way, if you're allowed negative r values here, then the plane would actually extend backwards this way. It wouldn't be like a half plane necessarily that shows in this picture here. Okay, and then the very last one, a constant z surface. Okay, so that would be obvious. That would be what? Planes parallel to the xy plane there. All right, that should do it for cylindrical coordinates. We'll be talking about integrating in cylindrical coordinates a little bit later. Okay, let's talk about another system of coordinates for 3 space called spherical coordinates. Spherical coordinates are really useful when you've got a figure that has origin symmetry. For 3 space, the coordinates are rho, theta, and phi in that order. These are defined in the picture below. Okay, what is rho? Rho is the distance from the origin to the point in 3 space. Theta is the regular polar angle that you would think of in cylindrical or polar coordinates. So imagine taking the point and projecting it down into the xy plane, and then forming the ray from the origin to that projected point in the xy plane. The angle between the positive x-axis and that ray is what we would call theta. What is phi? Imagine creating the ray from the origin to the point in question, and then forming the angle between the positive z-axis and that ray. The angle between those two would be what we call phi. Now notice here we're going to have this. Rho is always going to be greater than or equal to 0 by definition, and phi is always going to be between 0 and pi radians. Okay, these are true by definition. So with phi, we're not going to be, like the polar angle where you're able to have negative values for theta or add multiples of 2 pi or any of that stuff, okay? Or negative values for rho for that matter. All right. Now let's come over here. We're going to talk about conversion from spherical to Cartesian and vice versa, okay? The first thing that's very useful here, even though it's neither part of the spherical coordinate system nor the Cartesian, is little r, the little r from polar coordinates / cylindrical coordinates. I claim that little r is rho times the sine of phi. Now let's go back and look at our picture real fast here. If you guys see the little dashed triangle here in the picture, you can see that that's actually going to be what? a right triangle, and the angle between what? The vertical dashed line, orthogonal to the xy plane, and the actual ray from the origin to the point in question will end up giving an angle which is what? The same as the angle phi. And then from basic trigonometry, the side opposite would be what? What we're calling r, and then r divided by the hypotenuse rho would give the sine of the angle phi. Therefore, little r equals rho times the sine of phi. Okay, so that should be clear from the picture. Okay, that's useful because it makes it much easier to remember how to convert from spherical into Cartesian coordinates in the following way. You remember that it's basic that x equals r cosine theta. Now substitute for r the expression rho sine phi. Therefore, x equals rho sine phi cosine theta. And likewise, y equals r sine theta. Therefore, y equals rho sine phi sine theta. Now, for the z-coordinate, I claim it's rho cosine of phi. If we go back and look at our drawing once again, you notice that the z value in our dashed triangle, which can be signed, right? It could be positive or negative, but we would have what? This angle here being phi, that would be the side adjacent divided by the hypotenuse would be the cosine of phi. Therefore, z equals rho times the cosine of phi. And there we have it. Okay, so just have to stop and look at that picture there. Now, going the opposite direction here, going from Cartesian to spherical here, it's easy to see that rho would be what? The square root of the sum of the squares of x, y, and z. This simply goes back to the distance formula, right? Pythagoras, right? And the tangent of theta is y over x for non-zero x. That just goes back to what? Cylindrical polar coordinates. And then finally, to find phi, the easiest way to do that is go cosine inverse of z over rho. So supposedly you know x, y, and z. You compute rho, divide that into z, and then take the cosine inverse. That comes from this formula right here, that z equals rho times the cosine of phi, together with the fact you remember that cosine inverse always gives you an angle in the first or second quadrant, that is between 0 and pi. That's exactly what we want for our phi values here. So this is perfect. Okay, now let's look at a couple concrete examples involving numbers here. Example 1, convert from spherical coordinates 6, negative pi over 6, comma, pi over 4 to Cartesian coordinates. Here we've got rho is 6, theta is negative pi over 6, and phi is pi over 4. The solution is very easy. Just take those numbers and plug them back into our formulas here. So x equals rho sine phi cosine theta. So that's 6 sine pi over 4 cosine negative pi over 6. Put in the numbers, 6 times the square root of 2 over 2, square root of 3 over 2. Reducing, we get 3 square root of 6 over 2. Y would be rho sine phi sine theta. So that would be 6 sine pi over 4 sine negative pi over 6. So that would be 6 times the square root of 2 over 2 times negative 1/2. Reducing once again, we would get negative 3 square root of 2 over 2. Finally, z would be rho cosine phi. So that would be 6 times the cosine of pi over 4. So that would be 3 times the square root of 2. So our final answer, x, y, z, would be 3 square root of 6 over 2, negative 3 square root of 2 over 2, comma, 3 square root of 2. Now let's go the opposite direction, which is a little bit harder. Convert the Cartesian coordinates 3, 4, 12 into spherical coordinates, okay? Well, this isn't so bad, though. Let's compute rho. Rho would be the square root of the sum of the squares of x, y, and z. So that would be the square root of 3 squared and 4 squared and 12 squared. That turns out to be exactly 13. The tangent of theta, let's go y over x. Okay, how about 4 over 3? The tangent inverse of 4 over 3. That would do for us here because that's what? 3 4s in the first quadrant. 0.927 radians. Okay, finally phi. Phi would be what? We said cosine inverse of z over rho. We computed rho just above. So that'd be the cosine inverse of 12 over 13, which I found, I think, 0.395. So the answer would be 13, comma, 0.927, comma, 0.395. Okay, so there's a conversion into from Cartesian into spherical. Okay, let's look at the fixed coordinate surfaces for spherical coordinates. Suppose rho is fixed and we allow theta and phi to, be anything, okay, any allowable values. Then you see what we would get is the sphere centered at the origin with radius rho naught, as you see in the picture. Okay, in the middle one where theta is fixed, we get the same type of surfaces that we had before. We get what? A plane orthogonal to the xy plane containing the z-axis. And then finally, lastly, suppose that phi is fixed. Okay, so we've got a fixed angle there, phi naught. The set of all points in 3 space where phi naught is fixed would be what? Allowing, again, theta and rho to take on any values, we would actually get a cone, okay? A cone centered at the positive z-axis there, okay? So there we've got the fixed coordinate surfaces. Let's look at one last problem here. Example 3, convert z equals the square root of x squared plus y squared to spherical coordinates. Now, I'm just going to show you in this particular problem that sometimes, once again, it's nice to introduce the little r from polar cylindrical coordinates. Okay, let's go ahead and do that. Let's have the square root of x squared plus y squared equals r. That's going to be greater than 0. So the equation above becomes z equals r. But I want you to notice that in our formulas for spherical coordinates, that z divided by r would be what? Rho cosine phi. And we said r was what? Rho sine phi. If I take the ratio of those two, I actually get what? Cotangent of phi. Now, z over r is supposed to always be equal in our equation above, so our equation actually becomes what? Cotangent, of phi equals 1. Since phi has to be between 0 and pi, that means phi is always fixed at pi over 4. Once again, just like we were looking above, that's going to be what? A cone, right? If you guys measure down what? Phi equals pi over 4, that's going to give you a cone measured from the positive z-axis. Remember, that's going to give you a cone in 3 space. So, in fact, the equation of this surface up here, z equals the square root of x squared plus y squared, is actually a cone in 3 space. Okay? All right, we'll be looking at more of both of these coordinate systems as we go through and look at triple integration.